Hello and welcome back. In today's video, I'm overclocking the AMD Ryzen 7 8700G APU all the way up to 5350 MHz using the ASUS ROG X670E-I gaming Wi-Fi motherboard and EK Quantum custom loop water cooling. This APU is the successor to the 5700G, which I overclocked in SkatterBencher 26 or 27.
Incorrect.
Almost 2 years ago. APU overclocking is always interesting, to me at least, because these chips come with quite powerful integrated graphics. However, in this video, I'm focusing on overclocking the Zen 4 4nm cores inside the CPU, and I'll leave the IGP overclocking for another dedicated standalone SkatterBencher guide. Alright, let's jump into it. The Ryzen 7 8700G is the flagship model of AMD's Hawk Point desktop APU lineup. These processors were announced on January 8, 2024, a couple of days before CES. Hawk Point is the successor to the Ryzen 5000 Cezanne APUs launched in 2021. There are more than a few differences between these chips. As I said in the introduction, in today's video I'm focused on overclocking the CPU cores of this APU, and I'll leave the integrated graphics for a next SkatterBencher guide. The Ryzen 8000 series APUs come to market in two distinct configurations. The Ryzen 7 8700G and 8600G feature the Phoenix 1 die with Zen 4 cores, and the Ryzen 5 8500G and 8300G feature the Phoenix 2 die with a mix of Zen 4 and Zen 4C cores. A lot has been said about the difference between Zen 4 and Zen 4C cores. The point is that the core architecture is identical, while Zen 4C cores have a smaller footprint. The benefit is that you get more compute per area, but the trade-off is that you also have a higher hotspot temperature and lower frequencies. The Ryzen 7 8700G has 8 Zen 4 cores with 16 threads. The base frequency is 4.2 GHz and the listed maximum boost frequency is 5.1 GHz. The TDP is 65 watt and the TJ max is 95 degrees Celsius. In this video, I'm focusing on 4 different overclocking strategies. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The Alma Labs EFC is the older brother of the EFC SB, which I've used many times on this channel. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether or not the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure stability. A major selling point of the Hawk Point APUs is its integrated inference processing unit, basically its AI engine. I'm very interested in measuring the performance and maybe even overclocking the IPU, but unfortunately I couldn't find a suitable benchmark option at the moment of testing. It looks like IPU support may come to the AI benchmark that I'm using for all of my guides for quite some time now, but it's not here yet. For this guide, the AI benchmark performance results are basically those of the CPU cores. Before starting overclocking, we must check the system performance at default settings. The default precision boost 2 parameters for the Ryzen 7 8700G are as follows. Experienced Ryzen overclockers are familiar with most of these limiters. However, 2 are not that common: STAPM and HTF max. I will cover the STAPM limiter in more detail in my first overclocking strategy. The HTF max is a frequency limiter that kicks in when the CPU is running at a high temperature. It's not active on all Ryzen processors. On this 8700G, the HTF max lowers the maximum frequency when the temperature exceeds 85 degrees Celsius from the default 5150 MHz. The frequency decreases gradually to 5050 MHz at 95 degrees Celsius. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4063 MHz with 1.042 volts. The average CPU package power is 64.9 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4400 MHz with 1.136 volts. The average CPU package power is 69.5 watts. Of course, we can increase the maximum power consumption limit by using Precision Boost Overdrive, and that's exactly what we'll do in our first overclocking strategy. However, before we get going, make sure to locate the CMOS clear header. Shorting the clear CMOS header will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. The clear CMOS header is located on the ROG FPS2 card. In our first overclocking strategy, we take advantage of simply enabling Precision Boost Overdrive 2 and enabling AMD EXPO. With the launch of Zen 3, AMD introduced an improved version of their Precision Boost Overdrive Overclockers toolkit. This toolkit essentially allows end users, such as you and I, to fine-tune the performance of our AMD Ryzen CPU. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost Override and Scaler, Precision Boost Overdrive 2 also introduced Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we simply enable PBO, meaning that we rely on the motherboard's pre-programmed values to configure our power limits. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC limit will help unleash the frequency and multi-threaded workloads. A configuration option that is not really included in Precision Boost Overdrive but will still impact the power limits for our APU is STAPM, and that stands for Skin Temperature Aware Power Management. I talked about it briefly in my Raphael launch video when discussing how Precision Boost works. The STAPM limiter is primarily relevant for mobile devices. As the name implies, STAPM takes into account the device temperature for assessing the boost behavior. It represents the maximum power the processor can use within the thermal budget of the whole system. Since the Ryzen 7 8700G APU is a derivative of a notebook chip, it appears this STAPM limiter is also present. Usually we can disable STAPM in the BIOS, or the STAPM limit would change when we adjust any of the package power limits such as PPT or SPL. But in this case, it was a little bit more complicated as none of the usual settings did the trick. For this particular BIOS, the only way to adjust the STAPM limit was to adjust the sustained power limit in the Smart Shift control menu. Smart Shift is a set of AMD technologies that aims to optimize the power usage for mobile devices. Some of that technology enables dynamic power shifting between the CPU and the GPU depending on the workload needs, but it also includes shifting to power saving when the notebook is in battery mode. I'm pretty sure that in future BIOS releases, this STAPM power limiter will be adjusted using the other rules, but for the sake of this guide, I'll leave it in my BIOS configurations and I'll show you where you can find the option should you need it. EXPO stands for Extended Profiles for Overclocking, and it's essentially AMD's way to allow memory vendors such as G.Skill to program higher performance settings onto their memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. Upon entering the BIOS, switch to the Advanced Mode view and stay in the AI Tweaker menu. Set AI Overclock Tuner to EXPO 1. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Switch to the Advanced menu. Enter the AMD CBS submenu. Enter the SMU Common Options submenu. Enter the Smart Shift Control submenu. Set Smart Shift Control to Manual. Set Sustained Power Limit to 1 million. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We get a significant performance gain in all multi-threaded benchmark applications by enabling Precision Boost Overdrive. In addition, also lighter workloads see a small improvement from increasing the memory performance with EXPO. The highest performance increase is in AI benchmark with a plus 21.30% over stock performance. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4661 MHz with 1.263 volts. The average CPU package power is 137.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4773 MHz with 1.312 volts. The average CPU package power is 125.4 watts. We use the Shabino boost curve and knob bench to check the CPU's boost behavior and per core maximum effective clock frequency. The boost frequency at one active thread is about 5127 MHz and trails off to 4829 MHz when all cores are active. That is remarkably close to the chip's Fmax of 5150 MHz. Unlike with the previously overclocked AMD CPUs, we don't see a C-state boost limiter clipping the frequency when too many cores are active. We also find each of the 8 cores boosting to the Fmax of 5150 MHz. That's remarkable, as typically AMD CPUs would only have a few cores that boost to the maximum frequency. It's also promising, as this may indicate lots of overclocking potential. In our second overclocking strategy, we will tune the CPU's precision boost frequency boosting algorithm with the tools that are available in the Precision Boost Overdrive toolkit. Fused maximum frequency, or Fmax, is one of those performance limiters that's included in the Precision Boost algorithm. Essentially, the Fmax determines the maximum allowed frequency of the cores inside your CPU. Boost Clock Override, or Fmax Override, is one of the overclocking tools available in the PBO2 toolkit. It allows the user to override the arbitrary frequency limit between -1 GHz and plus 200 MHz in steps of 25 MHz. It's important to note that the Fmax override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. When we increase the Fmax boost limit by 200 MHz, the new Fmax is 5350 MHz. Scalar is another tool that's included in the Precision Boost Overdrive toolkit, and this tool allows you to override the warranted silicon stress level to achieve a higher frequency. You can adjust the maximum allowed fit level to 10 times higher than the factory fused limit. The effect of increasing scalar is that the Precision Boost algorithm should aggressively pursue higher voltages as it is less concerned with CPU lifespan. Usually the fit is not the limiting factor for achieving maximum performance. However, for this particular CPU, it helped me get slightly higher frequencies. Curve Optimizer is probably the most important tool in the Precision Boost Overdrive toolkit. Essentially, Curve Optimizer allows end users to adjust the factory fused VFT, or voltage frequency temperature curve. This VFT curve determines how much voltage the CPU should use for a certain frequency at a certain temperature. Of course, the higher the frequency or the higher the temperature, the more voltage is required. Curve Optimizer adjusts the VFT curve by offsetting the voltages of the factory fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. The traditional approach with Curve Optimizer is that we set a negative Curve Optimizer offset. Two things happen when you do that. First, we effectively undervolt the CPU and tell that it needs less voltage for a given frequency. As a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. In my Rafael launch video, I covered Curve Optimizer and Precision Boost Overdrive in depth. So feel free to check out that video if you want to learn more about these overclocking technologies. At the end of the day, per core curve optimizing has a tangible benefit because some cores inside your CPU has more headroom than other cores. The manual per-core curve optimizing process of a Ryzen CPU can become quite convoluted because it spans a wide range of workload scenarios, going from light single-threaded workloads all the way to heavy all-core AVX2 workloads. Usually when I'm overclocking a Ryzen CPU, I spend most of my time on this per-core curve optimizing. For this guide, I wanted to have a look at the OCCT stress test toolkit to see if I could leverage to find the best per-core curve optimizer settings. Switch to the advanced mode view and stay in the AI tweaker menu. Set AI overclock tuner to EXPO 1. Enter the precision boost overdrive submenu. Set precision boost overdrive to enabled. Set the precision boost overdrive scaler to enabled. Set customized precision boost overdrive scaler to 10x. Set CPU boost clock override to enabled positive. Set max CPU boost clock override to 200. Enter the curve optimizer submenu. Set curve optimizer to per core. Set core 0 to core 7 curve optimizer sign to negative. I set the curve optimizer for each core according to my test result. The curve optimizer results range from -50 to -25. Switch to the advanced menu. Enter the AMD CBS submenu. Enter the SMU Common Options submenu. Enter the Smart Shift Control submenu. Set Smart Shift Control to manual. Set Sustained Power Limit to 1 million. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. After the impressive curve optimizer Undervolt, I expected to see great improvements in performance. While the improvements are not hitting the highs I was hoping for, we do see a substantial performance uplift across the board. The highest performance improvement is in AI benchmark with an uplift of plus 24.93%. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4887 MHz with 1.237 volts. The average CPU package power is 137.2 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5053 MHz with 1.288 volts. The average CPU package power is 125.8 watts. We used the Shimano boost curve and knob bench to check the CPU's boost behavior and per core maximum effective clock frequency. The boost frequency at one active thread is about 5272 MHz and trails off to 5128 MHz when all cores are active. That's pretty impressive. Remember, the out-of-the-box advertised boost frequency is 5.1 GHz, and now we're getting slightly higher than that when all cores are active. Unfortunately, we also find that despite the aggressive undervolt with curve optimizer, we don't get any core to hit the new Fmax of 5350 MHz. That's a little bit surprising given all cores could hit the standard Fmax of 5.15 GHz. In the third overclocking strategy, we leverage the ASUS AI overclocking technology to squeeze more performance out of our CPU. For many years, motherboard vendors have tried to provide enthusiasts like you and I with automatic overclocking technologies to squeeze more performance out of our CPU more easily. However, most of the time that's a mixed bag because they rely on OC profiles. And those profiles are either too ambitious in terms of the frequency or they're too generous in terms of the voltage. ASUS AI overclocking is different than those technologies. Instead of working with a preset frequency and voltage profile, the system will monitor the CPU and cooling solution throughout an initial testing phase. Based on its findings, it will then predict the optimal settings. The system automatically guides the overclocking process and adjusts voltages and frequency to match your cooling system. The better your cooling, the higher your AI overclock. There are 3 steps to enabling AI overclocking. First, reset the BIOS to default settings. Then, reboot and enter the operating system. Run heavy workloads such as Prime 95, OCT, or Cinebench for 10 to 30 minutes. Then return to the BIOS and enable AI overclock when ready. In addition to automatic overclocking, AI overclocking provides advanced information and suggestions in the AI features menu. The information includes P0 VID and SP values for each CPU core, Precision Boost Overdrive 2 suggested overclocking parameters, and Dynamic OC Switcher suggested overclocking parameters. The overclocking suggestions are based on a continued evaluation of your CPU thermal solution. After enabling AI overclock, the following settings have changed. As you can see, AI overclock provides a conservative plus 100 MHz increase of the Precision Boost maximum frequency. It also boosts the CPU to 5100 MHz in an all-core workload by enabling Dynamic OC Switcher. Upon entering the BIOS, switch to the Advanced Mode view and stay in the AI Tweaker menu. Set AI Overclock Tuner to EXPO 1. Set CPU core ratio to AI Optimized. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. We get a pretty decent performance lift over stock by enabling AI overclock, but it's not as much as in our previous overclocking strategy. That's likely due to AI overclock not using Curve Optimizer. Still, we get a performance uplift of plus 17.65% in AI benchmark. When running the OCCT CPU AVX2 stability test, unfortunately, the CPU is not stable. AI overclock targets the typical use case and stability requirements, not a worst case scenario like an extreme all-core AVX2 workload. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5100 MHz with 1.216 volts. The average CPU package power is 114.6 watts. In the fourth and final overclocking strategy, I'm pursuing a manual overclock. Now, since the ASUS AI overclocking strategy didn't pass our worst case stress test, the OCCT with AVX2 enabled, I'd figure that's an ideal candidate for our benchmark, for our target for a manual overclock. And we can see how much frequency we can squeeze out of the CPU in our worst case scenario. But first, let's have a look at the Hawkpoint voltage and frequency topology. The clocking of Hawkpoint is similar to other AMD Zen 4 CPUs. The standard Hawkpoint platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides a CPU clock frequency granularity of 25 MHz. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. In a typical operation, all cores within a CCX will run at the same frequency. Since each CCX contains all 8 Zen 4 cores, all cores run at the same clock. However, the effective clock may differ if a core is in a different P state. The SoC PLLs includes a wide range of various PLLs. The ones most relevant for overclocking are the F clock, U clock, M clock, GFX clock, and IPU clock. The SoC PLLs are not particularly relevant for manual CPU core overclocking. Just like Raphael, Hawkpoint supports up to 2 external clock modes, in addition to the internal clock mode. From the voltage topology perspective, there are few differences between Hawkpoint and Raphael. Just like Raphael, the APU still relies on an internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDD-CR voltage rail provides the external power for 2 internal voltage regulators, VDD-CR CPU and VDD-CR VDDM. VDDR CPU provides the voltage for the CPU cores inside the CCX. The VDD-CR voltage rail can be directly controlled via the SVI3 interface using the CPU configuration. The end user can also directly control the VDD-CR voltage rail, as the motherboard BIOS provides the means to program the voltage regulator directly. On CPUs with a lot of cores, like the Ryzen Threadripper 7980X, which I overclocked on this channel a couple of weeks ago, per CCX manual tuning can become quite tedious because there are so many CCXs to tune. However, on this Ryzen 7 8700G APU, we only have one CCX. So that makes the process a lot faster and a lot simpler. Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So the first step in our tuning process would be to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CCX. Simply increase the ratio until the application shows signs of instability, then back off. No more, no less. In our case, we can push the CPU to nearly 5 GHz. Now that we know the ins and outs of Ryzen 7 8700G manual overclocking, let's jump into the BIOS. Upon entering the BIOS, switch to the advanced mode view and stay in the AI tweaker menu. Set AI overclock tuner to EXPO 1. Enter the CPU core ratio per CCX submenu. Set core VID 0 to 1.25. Set CCD 0, CCX 0 ratio to 49.50. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. As expected, we see a performance deficit against stock performance in single-threaded applications, as we lose the benefit of the precision boost 1T frequency when we manually overclock. In multi-threaded applications, however, we see a nice performance uplift up to plus 21.30% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4950 MHz with 1.219 volts. The average CPU package power is 140 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4950 MHz with 1.224 volts. The average CPU package power is 114.5 watts. Alright, let's wrap this up. As I said at the very beginning of this video, I always enjoy AMD APU overclocking. Not only because it has powerful integrated graphics that usually scale quite well with memory overclocking, but also because it's a different architecture. The APUs are monolithic designs. They're not based on chiplets. The Ryzen 7 8700G overclocking experience is very similar to that of all the other Ryzen 7000 CPUs. I was very surprised to see that each of the 8 cores in the CPU could hit 5.1 GHz at stock. That's the maximum frequency limit. Usually we don't see that. Usually we have a couple of cores that can hit it and other cores that can't. So I thought this is a great indicator that the overclocking will be huge. And the overclocking was huge when it comes to an all-core workload. After tuning, we could get all of our cores to run at more than 5.1 GHz. However, the maximum frequency wasn't that great. We could only push some cores to 5.3 GHz, so a really minor improvement. And that was despite a very aggressive per core curve optimizer tuning process. So that's a little bit disappointing. Anyway, that's it for me for this video. I am also going to have a look at the IPU once I find a suitable benchmark, and I'm also very keen to have a look at the Phoenix 2 die with Zen 4C chips, or Zen 4C cores rather. I want to thank you for watching, and I want to thank the patrons for their continued support. If you have any questions or comments, drop them in the comment section below. I will also have a written version of this guide up on my blog if you want to go through my settings or check out the screenshots of my stress tests, for example. And that's it. See you next time.